So today we'll start a new topic which is called spectral domain MoM. Spectral means you are actually doing Fourier transform. You do the calculation in the spectral domain in the Fourier transform domain. So usually what do? You take the Fourier transform of a time varying functions and you get the frequency domain. But here our fields are varying with respect to space. So the Fourier transform will be a little bit different here. When you have a fields which are varying with respect to space, when you do the Fourier transform, you will get it in the frequency domain, spectral domain. So this equation here is called basically here it's basically I have already told you if you want to find electric field or magnetic vector potential, you can find out from the Green's functions. Once you have the Green's function, you take the convolution of Green's function with the current density, you get the electric field. So depending on what equation you are solving, is it wave equation for electric field or magnetic field, your Green's function is going to be different. So let's say if you have a wave equation for electric field and you assume the source is a delta function and solve it, whatever function you are getting is the Green's function. And that Green's function, if you do convolution with the current density, you get the electric field. So this Green's function here is a electric dyadic Green's function. It will have 9 components. So till now we have discussed only Green's function, free space Green's function, which was exponential minus j beta r by 4 pi r. It was having only one component, or let's say here you will have 9 components. So I need to discuss this properly today, so that this is one of the very fundamental discussion we'll be doing today. Why do this Green's function have 9 components? So the symbol you have here is little bit different. So vector, you actually put an arrow here, but above the Green's function you have here, there's a double arrow. So when I have electric dyadic Green's function, I actually put a double arrow. This is no longer a vector, it's a dyadic, it's a dyad. So I'll discuss that, so you need not worry. It's just extension of vector analysis. There is something called dyadic analysis, which is an extension of the vector analysis. So the Green's function we are considering here is the electric dyadic Green's function. That is because we actually find electric field from the electric current density. So this Green's function we denote it by GEJ. E means we are actually finding electric field, J is the source. So the notation G subscript EJ means E electric field we are finding, the source is the current density. You can have many other types of electric dyadic Green's function, magnetic dyadic Green's function. Let's say if you want to find magnetic dyadic Green's function, that would be GM. So here it will be G magnetic field, let's say we denote magnetic field by B, then GBM, for example. So magnetic field we are finding from the magnetic current density. Those kind of notation would be there. But we'll use only GEJ here. Electric field we are finding from the current density. Current density is the source and we are observing the electric field. And this electric dyadic Green's functions you denote with the double arrow, not single arrow. So it is a dyad, extension of the vector analysis. And many of the students think that this is one of the very tough part of MoM. But as you do it again and again, you'll get used to it. So it will be just like vector later on. So this Green's function, electric dyadic Green's function will have 9 components. These are 9 components. I'll discuss that briefly in the next slide. So what do I mean by Green's function, which is also the impulse response of the system? Here it's the antenna, so impulse response of the antenna, let's say. So I already told you this Green's function will have 9 components. Forget about this tilde here. Tilde means we are in the spectral domain. So in the previous one, I did not put any tilde above the G here. G is with the double arrow. It's a dyadic Green's function. In the space domain, when I take for a transform of that, I get the spectral domain Green's function. So for spectral domain MoM, I need to find out spectral domain Green's function. So when I take Fourier transform of this, I will get the Fourier transform domain. In the Fourier transform domain, I usually denote the Fourier transform domain with the tilde. So tilde here means it's in the Fourier transform domain. Just before that, let us try to see why this Green's function is having 9 components. We want to find electric field. Electric field is what we are observing. J is the current density, which is the source. So now you assume this setup here I have shown here. In this setup, usually what you have, as I've already told you before also, we have a source and we are observing the fields. Source is the current density. Okay, so let's say source is somewhere here. We actually denote all the source which is producing the fields with a Diaz variable. Diaz here, Diaz here, Diaz here. So with the prime coordinates, we denote the source. Without the prime coordinates, unprime coordinate x, y, z. Let's say source is somewhere here. So we have an arbitrary source at the location P dash, which is having a coordinate of x dash, y dash, z dash. And we are observing the field produced by this source at a location O. And this location is denoted by x, y, z. So we have two coordinate systems, one for the source and one for the observation. So now the source coordinates are denoted by x dash, y dash, z dash. Observation coordinates are denoted by x, y, z. Source would be, in our case, is the current density. J current density is the source and observation is the electric field. So let's say okay, I should have drawn this current. See, basically the source current, if I assume that the source current is directed along the x-axis. If I assume that there is a delta source current which is directed along the x-axis, it's a vector. It's a vector, its direction along the x-axis. I can make observation at this point observation. I can have first observation. So I have a source, let's say at the origin. I have shown it at arbitrary point. Let's say I have a source at the origin and this source is a delta function and directed along the x direction. So x hat means is the unit vector along the x-axis, y hat means unit vector along the y-axis, z hat means unit vector along the z-axis. Assume a source, arbitrary source located at the origin and that's a delta source and it's directed along the x-axis. I can observe at point O for 3 different cases. First, I can observe the field along the x-axis because of this delta function directed along the x-axis. So that field is called GXX. GXX is the electric field we are observing at the point observation point O, and its observation is along the x-axis, and the current density we are considering is along direction is along the x-axis. When I have a delta source whose direction is along the x-axis and I observe the field along the x-axis, what I get is GXX. That's the Green's function, impulse response of the system. So the source should be a delta function. Now I am assuming a source which is directed along the x-axis and I am observing the field along the x-axis. Whatever field I am observing is GXX. And I can also observe this field along the y-axis. I have the same source, delta source directed along the x-axis. I am observing the field along the y-axis. That is called GYX. X is the source, Y is the observation direction. Similarly, for the same source, I can also observe along the z-axis. That is called GZX. Source is along the x direction, delta source is along the x direction, I am observing the field along the z-axis. Similarly, I can also have a source which is directed along the y-axis, delta source directed along the y-axis. If I observe the field along the x-axis, then what I am getting is GXY. Source is directed along the y-axis, observation is along the x-axis. And I can also make observation along the y-axis. Source is directed along the y-axis, and I'm also making observation along the y-axis. What I'm getting is GYY. Similarly, source is directed along the y-axis, but I'm observing along the z-axis. What I'm getting is GZY. Similarly, I can also have a source which is directed along the z-axis, and I make observation along the x-axis. Then what I'm getting is GXZ. And I can also make observation of this source directed along the z-axis, along the y-axis. What I'm getting is GYZ. I can have a source which is directed along the z-axis, and I'm making observation also along the z-axis. What I'm getting is GZZ. But the source we are considering here is a delta source. So this is the impulse response of the system, and you know that impulse response of the system is the Green's function. So that's why we have 9 components of the Green's function, and dyadic Green's function is a compact notation of these 9 components of the field. So here we have 9 components of the field. Dyadic Green's function can note down these 9 components easily with this symbol here. This is a dyadic way of noting down the 9 components of the fields. Okay. But most of the time, we actually neglect the thickness of the metal. Let's say you have a metal microstrip antenna, any kind of metal printing. The metal thickness is very thin. So the variation of the field along the z-axis, you can neglect it. So if you assume that metal is very thin, most of the time metal's thickness is around some micro, some 37 micro or something like that. So the thickness of the metal is very thin, so you just consider x and y plane, you neglect the z-axis. In that case, all the z dependence of the Green's function would be gone. And most of the time, when you consider method of moments, you doesn't consider the volumetric analysis. You actually analyze method of moments for the surface. So there, you can just consider xy plane, you can neglect the z-axis, which is the thickness. In that case, among the 9 components, you just need to worry about those components which are independent of z. So when you note down, what you can observe is that in that case, you'll have only gxx, gxy, gyx, gyy. So with this measure simplification, you just need to worry about the 4 components of this electric dyadic Green's function, and it works fine. There will be a slight change in the result, but that is negligible. We have observed that when you neglect the thickness of the metal, the change in the solution you get for the fields is not much. Okay, so this is the structure we'll be considering. It's a multi-layered structure, layer by layer. So you have layer 1. So layer 1 is having material parameter of mu1 epsilon 1. Layer 2 would have material parameters of mu2 epsilon 2. Nowadays you have that multi-layer structures. Let's say in silicon structures, all the structure, planar structure, you stack it one by one, layer by layer. So we are trying to analyze those kind of structure, printed circuits. Printed circuits layer by, we will have one substrate, another substrate, silicon layer, then silicon dioxide layer, or those kind of structures. Printed structure we'll be considering. We are considering any general one-dimensional multi-layer structure. Here you have n layers, layer 1, 2, 3 up to layer n, which is stacked along the z-axis. So this is the z-axis, this is the y-axis, and this is the x-axis, which is shown here with the cross here. That means x-axis is going into the surface of your screen, computer screen. Okay, so this is the multi-layered structure. You have n layers. Every layer will have different material parameters. In electromagnetics, we actually define material parameters in terms of mu and epsilon. Mu is the magnetic permeability, epsilon is the electric permittivity, and mu will give you the magnetic properties of the material, epsilon will give you the electric properties of the material. So every substrate, every layer will have different values of mu and epsilon. Depending on the material you are choosing, mu and epsilon is going to change. Assume that at any arbitrary point, any layer, let's say ith layer, you assume that there is a current density here. So the source for radiation for most of the antenna is the current density. So when you supply a conductor or any material with a time-varying current density, it will start radiating. Then only will have radiation. So you assume that there is a current density, arbitrary current density J in the ith layer, which is shown here. We are supposed to find the Green's function for this multi-layered structure. And this can be easily done in the spectral domain by considering the equivalent circuit like this here. So this has been derived actually, and this the equivalent circuit. It has been verified in one of the classic paper in the IEEE transaction on microwave theory and techniques. If you are interested, I can give you that. So we have a multi-layered structure. So what is this model? So in this equivalent circuit model, every layer would be modeled by a transmission line. Layer 1 would be modeled by a transmission line. Layer 2 will be modeled by another transmission line. Every layer, n layers, will be modeled by a transmission line. So now for every layer, since mu and epsilon is changing, the impedance of the transmission line is going to change. Characteristics impedance of the transmission line is going to change. It is dependent on the material parameter of every layer. So first layer would be having different characteristics impedance, second layer, third layer, and so on. Here we have two models. One is T model, another is TM circuit models. In the T model, Z1 is going to be different. In TM model, Z1 is going to be different. So we usually denote for T model, characteristics impedance of the line is Z1 TE for the first layer, and for the TM model, we consider the characteristics impedance of the first layer as Z1 TM. For the NF1, Zn TE and Zn TM. So we will have two equivalent circuit model of the same structure, multi-layer, one-dimensional multi-layer structure for T modes and TM modes. And I know that all of you know what is T mode and TM modes. T means transverse electric. Transverse means perpendicular electric. Electric field will not have any component along the direction of propagation of the wave. Electric field is perpendicular to the direction of propagation of wave. Let's say electric field is propagating along the z-axis, then electric field will not have any component along the direction of propagation of the wave. Similarly, TM means magnetic field will not have any component along the direction of propagation of wave. So if magnetic field is propagating along the z-axis, magnetic field will not have any z component for TM case, and if electric field is propagating along the z-axis, electric field will not have any component along the z-axis. So you have two models. One is T model, another is TM model of that multi-layered structure we have considered here. N layer, N transmission line with different characteristics impedance for T modes and TM mode. And you can calculate this characteristics impedance for T and TM mode from the mu epsilon parameters. And don't forget that we have a source. We have a source at the ith layer. Ith layer, we have a current density. So now that current density can be replaced by a 1 amp current density, which is shown here, because we want to find the impulse response of the system. We assume that there is a 1 amp current here, and we'll find the Green's function. Then if you want to find the electric field for any arbitrary current, then you do the convolution with the Green's function, then you'll get the electric field for any arbitrary current. So this is how you find the Green's function in the spectral domain. So from the equivalent circuit model, you can find out the Green's function for the T and TM circuit model. So here, what you need to do is you need to find out what is the voltage for T and voltage for TM. So you need to find out the voltage for T mode and TM mode at arbitrary location. So that I will discuss later on. So you need to find out two things, voltage for the T mode and TM mode. And once you have the voltage for T and TM mode, you can find out Green's function. And we are considering only four components of the Green's function, Gxx, Gxy, Gyx, and Gyy, because we have neglected the thickness of the metal. How to find this, I will discuss later on. So this has been derived in that paper. I've told you, that classic paper. If you want, I can give it to you. So just find this voltage along the transmission line for T case and TM case, then that's all. From this equivalent circuit here, you find out voltage for T case and TM case, then you can find out the Green's function. That's very easy. So just before that, let us do a little bit of dyadic analysis. What is dyadic analysis? Here, what do you have? You have K vector. K vector is KT vector, T for transversal perpendicular plane. K vector, you are doing cross product with Z vector. So this will give you another vector. When I do cross product of two vectors, I get another vector. Here again, I'm also doing cross product of KT with Z, I will get another vector. So here you have, in a way, so let me just go back to, let's start from here. For example, you have KT hat here. These are two vectors. So what is a dyad? Dyad is basically juxtaposition of two vectors. When you place two vectors, then you get a dyad. So what is this dyad? Let us try to see. So dyad is basically juxtaposition of two vectors. When you place one vector with another vector, then you get a dyad. So what is a KT vector? KT vector will have X component and Y component. So KXX hat plus KYY hat and it's a unit vector. So kt head means whenever I put a head here, it's a unit vector. What we have here in this expression is kt head cross product with z head. So what is kt head? Kt vector is kx x head plus ky y ds. We are considering only xy plane, so this wave vector will have only x and y component, but I am interested in the unit vector of that, so I need to divide by the amplitude of this wave vector, so square root of kx square plus ky square. So I do the cross product with the z vector. So this is the kt vector unit vector and this is the z unit vector. When I do cross product of these two vectors, I simply get ky x head minus kx y head. And here same thing here also. I get cross product of kt unit vector with z unit vector. I get ky x head minus kx y head. So this is what I'm getting. So here also I do the juxtaposition of kt unit vector with kt unit vector. So kt unit vector is this. Kt unit vector is this. When I just see how do I do dyadic analysis. Let's see. When I multiply this with this, what I get is this vector and this vector. When I multiply it, kx x hat kx x hat, what do I get? Kx square x hat x hat. So I'm just positioning two vectors here. This is just a simple notation where I just a position of two vectors. This is a dyad here. Similarly, when I multiply this with the ky y hat, what do I get? Kx ky x hat y hat. This is another dyad. And when I do multiplication of this with this, what do I get? Ky x hat y hat x hat. Then ky square y hat y hat. That's how I get it. So I can combine the terms. Finally, what I get is Green's function in the spectral domain, which will have four components. I can clearly see that I will have only four components here. One is x hat, one is y hat, one is y hat x hat, another is x hat y hat, another is y hat y hat. So I will have only four dyads here. So you can combine this term here, similar terms x hat y hat y hat, xy y hat plus y hat x hat plus y hat y hat. So you combine those terms, then finally what you get is something like this. So the Green's function here will have only four components. One is x hat component, and this y hat x hat component, and this x hat y hat component, and this y hat. So once you know this voltage here, you know this voltage here, you know what is kx, ky, you can find out the Green's function. All you need to do is find out this voltage here for T case and Tm case. So finally, the Green's function expression for x and xy and yx and yy turns out to be this. We just need to find out this voltage for T and Tm case from the equivalent circuit model. So let us take simple examples to find out how do you find out that voltage and use this formula and find out the Green's function xx, xy, yy and yx component. So let us consider a simple structure. Let's say you have a patch antenna. Patch antenna is basically you have a metal printing. This is the patch. You print, it could be pads or it could be filter or it could be any kind of microstrip circuits. Microstrip circuits are printed circuits which are metal printing. This structure here with the brown color is basically a metal. You are printing this over a substrate. It could be FR4 board, PCB board, it could be silicone substrate, it could be germanium substrate, any kind of substrate. You print it, and here also you have a metal ground. But let's assume that there is no metal here. You just have a substrate and you are printing a metal here. And usually we use this for analysis of an antenna which is called printed monopole antenna, which is a variant of the microstrip antenna. In the microstrip antenna, you have a ground plane here. But for the printed monopole antenna, see, basically microstrip antenna has a very narrow bandwidth, usually 5%, 7%. But if you remove the ground plane below the microstrip antenna, you have something called printed monopole antenna. We have done a lot of research in that. And when you remove the ground plane below the patch antenna, the bandwidth of this microstrip antenna can be ultra wideband, super wideband. It can have bandwidth greater than 100%. Percentage bandwidth can be even greater than 100%. That's actually a big achievement. When you remove the ground plane below the microstrip antenna, you have a bandwidth which is super wideband. We have done a lot of research in that. My third PhD student, we have done a lot of antennas which has super wideband. So those kind of antennas are called printed monopole antennas, where you don't have a ground plane here. You just have a substrate. It could be FR4, could be roser substrate, any kind of substrate. You print a metal on that, different structures depending on the antenna you are designing. So you have metal layer here, you have substrate layer here. So then above this you have a free space. Below this also you have free space. So how many layer structure is this? So now this layer, you call it layer 0, which is below the substrate. We have considered multi-layer structure along the z-axis. You assume that this is z-axis. We have one layer which is a free space below this substrate. So obviously free space will have material parameter of mu naught and epsilon naught. This layer we call it layer 0. Then you have the substrate layer. Substrate layer usually have epsilon as epsilon 0 into epsilon r. Epsilon 0 is the electric permittivity for free space, and epsilon r is the relative permittivity for this medium. For example, if you have a FR4 substrate which is used for printed circuit boards, this epsilon r will be 4.4. And most of the dielectric will have mu as mu naught. Only magnetic material will have different values of mu. Otherwise, if you have a dielectric, then mu will be just mu naught. Same as that of the free space. So you have a layer 0, then you have a layer 1, which is substrate. And here, this metal here, you are going to supply some time-varying current, then only this will start radiating. Or let's say you want to design a filter also, you are supplying some signal here. That signal can be represented, whenever you have metal, you can represent it by a current density. Whenever you have a slot, or whenever you have a aperture, you can represent it by a magnetic current density. But here we have a metal here. This antenna is made up of metal. So we can represent it by a current density here. So I have replaced this metal by a current density. Above this also we have a free space. We'll call that as layer 2. That is actually free space has a material parameter of epsilon 0 and mu 0. So we have a 3-layered structure. The structure we have considered was general case when I have a net layer, but here we have just 3 layers. One is free space, another is substrate layer, then another is free space, and we have a source here at this interface between layer 2 and layer 1. So for this case, I will try to find out the Green's function. So let us look at the equivalent circuit here. I have a source here at z is equal to, let's assume that this is z is equal to 0. Z is equal to 0 is this. Z is equal to ice is this. Ice is the thickness of the substrate. So this is z is equal to 0 at a thickness of z is equal to ice. I have a substrate, then I'm printing a metal here. So now let us find the T and TM circuit model for this 3-layered structure. So here for this 3-layered structure, layer 0 is a free space. Layer 1 is a substrate. So layer 1 I can represent it by a transmission line. For the T case, it will have a characteristic impedance of Z1T. For the TM case, it will have characteristic impedance of Z1TM. So at Z is equal to 0, I have a free space. Free space, what is the impedance for the free space? So when you send out signal from your antenna, antenna will see free space is having a specific impedance. That impedance is called the intrinsic impedance of the free space. Intrinsic impedance, so you can model this free space by a impedance of 377 ohm. That is your eta naught. Eta naught is 377 ohm. So you can replace the free space by a impedance of 377 ohm, Z naught T. And we also have another free space. We can represent it by Z naught T, which is of 377 ohm. And at the interface between layer 1 and layer 2, I have a current density. So I want to find impulse response of the system. I assume that that current density is of 1 amp. Similarly, for TM case also, I assume that there is a current density of 1 amp at the interface at Z is equal to H. H is the thickness of the substrate. And above that, I have a free space. I will denote it by wave impedance of the free space. Then at Z is equal to 0 and Z is equal to H, I have a transmission line, which is a substrate, and characteristic impedance is Z1TM. And below that, I have a free space. I will denote it by Z0TM. That's a wave impedance for a free space. So this is the equivalent T and TM circuit model of the 3-layer structure, which is for the printed monopole antenna. So from this equivalent circuit, I can find out what is the voltage. In order to do that, I need to make an observation of the impedance along the upper portion. So let's call that this is the interface. I look at the impedance up. I will denote it by Z up. This is for the T case, so Z up T. And if I look down, then I will denote it by Z down T. Similarly, for the TM case also, When I look at the impedance up, I will denote it by Z up Tm, and when I look down, I will denote it by Z down Tm. So if I know these impedances, then I can find out the voltage. So when I look up from here, Z is equal to H. When I look up from here, what do I see? I just see an impedance of Z naught T. Similarly, also when I look up here what is the impedance? I just see an impedance of Z naught Tm. So Z up T is Z naught T and Z up Tm is Z naught Tm. You can find out Z naught T as K naught eta naught by beta naught. Z0 Tm as beta naught eta naught by K naught. What is beta naught? Beta naught is square root of K naught square minus Kc square. Kc square is Kx square plus Ky square for this case. So Kx and Ky was the propagation wave vector along the x-axis and y-axis. K naught is the wave vector for the free space. K is 2 pi by lambda. Lambda is the operating frequency, operating wavelength in which we are considering this analysis. So once I know lambda, once I know the frequency at which I'm making an observation, I know what is lambda. Lambda is C by F. Once I have lambda, I can find out what is K naught. K naught is 2 pi by lambda. Kx and Ky are the wave impedance, wave vector along the x-axis and y-axis. I know what is beta naught. I know is K naught. I know what is eta naught. Eta naught is 377 ohm. K naught is 2 pi by lambda. Beta naught I can find out from here. I can find out what is Z up T and Z up Tm. How about Z down T and Tm? So when I look down from here, I see a transmission line of length H and it is loaded with this Z naught T. Similarly, also when I look down, I have a transmission line and it's loaded with a Z naught Tm. So you know that you can find out. See, when I have a transmission line loaded with this load here from the impedance transformation formula for transmission line, so I can easily find out. So when I have a impedance looking down, what I'm seeing is it's terminated with the free space, so I can find out what is Z load. Z load is Z naught T. So if I want to find input impedance of a transmission line loaded with ZL, what do I do? Z naught ZL plus JZ naught 10 beta L plus, that's a standard formula you have from transmission line analysis. So here, what is the load? Load is Z naught T for the first case. What is the load? This is Z naught T. So I will just replace it. Load would be Z naught T, Z naught T. What is the characteristic impedance for this case? Z1T. So what is the characteristic? Z1T, Z1T, Z1T. So I have the standard formula. I just replace the characteristics impedance by Z1T and the load by Z0T. Similarly, for TM case, I will replace the characteristics impedance by Z1TM and load by Z0TM. So when looking down, this is the impedance I am seeing looking down. Looking up, we have already done that. Just note that here Z1T characteristics impedance can be found out as K1 eta 1 by beta 1. K1 here is K naught and eta 1. So this K1 eta 1 again you can find it as K naught square root of epsilon r eta naught and beta 1 divided by beta 1 is square root of epsilon r. See what is eta 1? Eta 1 is the impedance, wave impedance of the substrate medium. So you can find out eta naught as eta 1 as eta naught by square root of epsilon r and K1 is K naught epsilon r. So finally what you get is Z1T is K naught eta naught by beta 1. Similarly, you can find out Z1TM as beta 1 eta 1 by K1. What is eta 1? Eta naught by square root of epsilon r. This is for the substrate and substrate has epsilon r. What is K1? K1 is K naught square root of epsilon r. Epsilon r is the relative permittivity of the substrate. Finally, you can find out Z1T and Z1TM. You know what is Z0TM, Z0T. You can find out what is Z down T and Z down TM. So now, this is basically impedance looking up and impedance looking down. So what is the equivalent impedance here? Then it's basically a parallel combination of the impedance looking up and looking down. So if I want to find the equivalent T and TM case, I just have the parallel combination of Z down and Z up. Here also for TM case, Z down and Z up. So equivalent impedance you can find out. Once you have the equivalent impedance, you can find out. So this is the major simplification for the equivalent T and TM case I have derived it. See, basically you can derive it from this formula you have here. You have Z down T, Z down TM. You can derive it, then final expression I have got it is basically K naught eta naught 1 by DTE. So the final expression looks like very simple, k naught eta naught 1 by dte. So dte I have denoted for TE case, d is the denominator, this is the expression for dte. Similarly, Z equivalent Tm is eta naught beta naught by k naught dTm. dTm is this expression here. I have simplified it. After simplification, I am getting a very simple expression for Z equivalent for T and Tm case. In the Z equivalent for T, I am getting a function in the denominator which is dTe, and what Z equivalent for Tm, I am getting a function which is dTm given by this. So now I have the expression for the Green's function, xx component, xy component, yy component. And in this case, look at this equivalent circuit here you have. If I know the equivalent impedance here, if I multiply that equivalent impedance with the 1 amp current, then I get the voltage at this location. I'm interested in finding the voltage at this location. I know what is equivalent impedance at this location. I know what is the current here. When I multiply those two, what I'm getting is the voltage at that location. So current is anyway 1 amp. If I know what is Z equivalent here, that would be the voltage at this location. So that's how I'll find voltage here. See, voltage for T case and Tm case, I know the equivalent impedance for T and Tm case, that would be the voltage because anyway the current is 1 amp here. So I can just substitute the value of VTE by ZTE and VTM by ZTM, then I can find out the Green's function for component XX, XY, YY. The final expression for GXX and GXY, GYY. It has been observed that GXY is equal to GYX. Here you have new notation here, K rho square is KX square plus KY square. How much time do I have? Okay, I'll stop here because we'll have a lot of discussion.